Hey everyone, and welcome to the Deep Dive. We get tons of great questions from you all, and today we're diving deep into one that's been popping up a lot lately. It's all about the RT-PCR test, the one used to detect SARS-CoV-2.
Right. Lots of folks are curious about this test and how it actually works.
Exactly. And we've got some really interesting source material for this deep dive. There's a scientific paper out there, along with an addendum that really digs into the nuts and bolts of the test.
It's a pretty detailed critique, actually.
Yeah, and some of the stuff they found is, well, a little unsettling, to say the least.
That's putting it mildly. For starters, they point out that the original design of the test was based on computer simulations, not real virus samples.
Hold on. They designed a test for a brand new virus based on what a computer spit out.
Well, yeah. At the time, remember, they didn't have actual virus samples readily available.
Okay, that makes sense, I guess, given the urgency of the situation.
Right. So they used genetic sequences from a lab in China and just sort of assumed that this new virus would behave similarly to the 2003 SARS virus. So they kind of worked off a blueprint, hoping it would be a close enough match.
You got it. But, as the paper points out, that kind of approach comes with some inherent risks. There's this thing called cross-reactivity, where the test might pick up other viruses or genetic material that just happen to be similar to SARS-CoV-2.
So, like, it's mistaking a shadow for the real deal.
Exactly. And that's just one of the issues they uncovered. The paper also takes a close look at the primers used in the test.
Primers, remind me what those are again?
Sure, primers are like tiny little genetic guides that help the test zero in on the specific RNA sequence they're looking for.
So they're like those sniffer dogs they use at airports, trained to find a specific scent.
Great analogy. But here's the thing. The paper points out that the concentrations of primers used in this test are unusually high.
So, like, they're sending in a whole pack of sniffer dogs when they only need one.
Kinda. And too much primer can lead to what we call non-specific binding. It's like those dogs getting distracted by every scent they come across and barking at everything.
So the test might start picking up things that aren't actually the virus.
Exactly. And there's another issue with the primers. They used these kind of wobbly sequences with letters like W, R, M, and S instead of the usual A, T, C, and Gs that make up DNA.
Wobbly sequences? I've never heard of those before. What do they do?
Well, those letters mean that different base pairs could be present at those positions, so there's not just one exact match the primer's looking for.
So it's like having a key that can fit into multiple locks, not just the one it's supposed to.
You got it. And that lack of specificity can really throw things off. It increases the chances of the test latching on to something it shouldn't and giving a false positive result.
Yeah, I can see how that would be a problem. So we've got these wobbly primers that might be too sensitive, and they're based on computer simulations rather than actual virus samples. Anything else we need to know about this test?
Oh, there's more. They also found issues with the temperature control during the testing process.
Temperature? What does that have to do with it?
Well, there's this thing called annealing temperature, which is the temperature at which the primers actually bind to their target RNA sequence.
Okay, so the temperature has to be just right for those sniffer dogs to do their job.
Exactly. But the paper found that the annealing temperatures used in the Corman-Drosten protocol were all over the place. Sometimes there was a difference of as much as 10 degrees Celsius for the same primer pair.
10 degrees? Wow, that's a pretty big difference.
Yeah, and those discrepancies can cause even more non-specific binding, making the results even less reliable.
So we've got shaky foundations with those computer models, those overly enthusiastic primers, and now temperature issues on top of it all. This isn't looking so good for the RT-PCR test.
And wait, there's more.
Oh, no, don't tell me. What else did they find?
Well, the cycle count, also known as the C-Kate value, it's basically the number of times the test amplifies the genetic material to try and detect the virus.
Right, I remember hearing about that. Doesn't a higher C-Kate value mean there's less virus present?
That's the general idea. But here's the kicker. The Corman-Drosten paper doesn't actually specify a cutoff for what C-best value constitutes a positive or negative result.
Wait, so different labs could be interpreting the same C value in totally different ways?
Exactly. There's no standardization, so one lab might call a sample positive at a CEAP of 35, while another lab might call it negative at the same value.
Oh, wow, that seems like a recipe for chaos and confusion.
To make matters even worse, there's research suggesting that at a CDAT value of 35, less than 3% of cultures actually had live virus.
So you could be testing positive but not actually be infectious.
That's the concern. And if labs are running the test with 45 cycles, as recommended by the WHO, then a lot of those positive results might be from non-infectious viral fragments.
Okay, so we've got this cycle count conundrum on top of all the other issues. I'm starting to wonder if there's anything good about this test at all.
Well, that's a great question, and it leads us to the next big concern raised by the paper: validation.
Validation, you mean like making sure the test actually does what it's supposed to do?
Precisely. It's like double-checking your work to make sure you didn't make any mistakes. And in science, validation is absolutely crucial, especially when you're talking about a diagnostic test.
So what kind of validation are we talking about here? Did they not test the test?
Well, they did some testing, but the critique points out that they didn't do any molecular validation of their results.
What does that mean, molecular validation?
Basically, it means they didn't actually confirm if what they were amplifying was truly the SARS-CoV-2 genes.
So they might have been picking up all sorts of other stuff and calling it a positive result.
That's the worry. They didn't go back and double-check to make sure they were actually seeing what they thought they were seeing.
Okay, so we've got 4 strikes against this test already. Questionable foundations, those overzealous primers, temperature issues, and now this lack of validation. I have a feeling this deep dive is about to get even deeper.
You could say that again, and trust me, there's still plenty more to unpack.
All right, well, let's take a quick break, and then we'll dive right back in and see what other surprises this paper has in store for us.
Sounds good to me. We'll be back in a flash. All right, so where were we? Ah, yes, those pesky primers and the whole validation thing.
Right. So much for that gold standard of testing, huh? But remember, we're not done yet. We've got that addendum to dig into.
Oh yeah, that addendum. It's like the cherry on top of this whole critique sundae.
So it's basically adding even more fuel to the fire.
Exactly. It summarizes findings from other scientific papers that have looked at the Corman-Drosten protocol, kind of like a peer review of the peer review.
So it's like a whole team of experts double-checking the work, making sure nothing was missed.
You got it. And they found a lot to talk about. Out of the 20 publications they reviewed, 17 of them found problems with the Corman-Drosten PCR protocol.
17 out of 20. Wow, that's a pretty clear sign that something's amiss.
It's not just 1 or 2 outliers. It's a pretty consistent pattern. And these studies documented a whole bunch of issues: false positives in negative control samples, lower sensitivity compared to other tests, you name it.
So it's not just this one paper raising a red flag. It seems like a lot of researchers are finding similar problems.
Exactly. It's like going to 5 different mechanics, and they all tell you your car needs a new transmission.
Okay, so we've got all this evidence stacking up, suggesting that the RT-PCR test might not be as reliable as we thought. But what does that mean for the big picture?
Well, that's the million-dollar question, isn't it? I mean,
Okay.
we've been using this test for everything: tracking the spread of the virus, making decisions about lockdowns, travel restrictions, you name it.
Right, it's been a cornerstone of our pandemic response for years now.
And now we're finding out that the cornerstone might be a little cracked.
So are we saying we should just toss out all the data we've collected and start from scratch?
Not necessarily. It's more about being aware of the limitations of the data and interpreting it with a healthy dose of skepticism.
So kind of like taking everything with a grain of salt.
Exactly. We need to be more cautious, look for corroborating evidence, and be transparent about the uncertainties.
Okay, that makes sense. But what about solutions? If this test is so flawed, what can we do to improve the accuracy of COVID-19 testing going forward?
Well, for starters, we need to address those flaws in the existing RT-PCR tests. Revising those primers, setting clear cutoff values for the cycle count, things like that.
So it's like fine-tuning the recipe to make sure everyone's baking the same cake.
Exactly. We need more standardization and quality control across the board.
Yeah.
But we also need to look beyond the RT-PCR test and explore other testing methods that might be more accurate and specific.
Like what? Are there other options out there?
Absolutely. There are other molecular diagnostic techniques that might be a better fit, things like isothermal amplification methods and next-generation sequencing.
Those sound interesting. What are the advantages of those methods?
Well, isothermal amplification, for example, doesn't require those temperature cycles that PCR relies on. It's simpler, faster, potentially more cost-effective, and less prone to contamination.
That sounds promising. What about next-generation sequencing? What's that all about?
Next-generation sequencing, or NGS, allows us to look at the entire genetic code of the virus, not just a small snippet like PCR does. It's like upgrading from a magnifying glass to a high-powered microscope.
So get a much more detailed picture of what's going on.
Exactly. NGS can help us spot new variants, track how they spread, and even develop more targeted treatments and vaccines.
These other methods sound pretty amazing. Why aren't we using them more widely already?
Well, there are some challenges. Cost and infrastructure are big ones. NGS, for example, requires specialized equipment and expertise that not all labs have access to.
So it's like having a fancy new sports car. It's great, but not everyone can afford it or has the roads to drive it on.
That's a great analogy. But just like any new technology, as these methods become more refined and accessible, I think we'll see them play a bigger role in our pandemic response.
Okay, so we've talked about the problems with the RT-PCR test, the need for cautious data interpretation, and the potential of these other testing methods. But what does all of this mean for the average person who's just trying to stay informed and make safe choices during this pandemic?
That's a great question. I think the main takeaway here is that no test is perfect and no data is absolute.
So we need to be critical thinkers, not just blindly accepting whatever we're told.
Exactly. Question the information you're given, seek out multiple sources, and remember that science is always evolving.
What are some practical things people can do to be more informed about COVID-19 testing and data?
Well, always ask about the type of test being used. If it's an RT-PCR test, find out about the lab's procedures and their cutoff value for the cycle count. It's like being a savvy consumer, doing your research before you buy something.
And when it comes to data, what should we be looking out for?
Stick to reputable sources, like government health agencies or respected research institutions. Be wary of sensational headlines or statistics that sound too good to be true.
And always remember, context is key. A single data point doesn't tell the whole story.
Absolutely. Look for trends over time, compare data from different sources, and be aware of the limitations of the data collection methods. It's like being a detective, piecing together the evidence to get a clearer picture.
So we all need to become amateur epidemiologists.
In a way, yes, but you don't have to go it alone. There are lots of resources out there to help you understand the data and make sense of the science.
What are some good resources people can turn to?
Well, government health agencies like the CDC and the WHO are great starting points. Universities and research hospitals often have excellent websites and publications that explain things in bleak language. And don't underestimate the power of a good science journalist.
Those are all great suggestions, but what about all the conflicting information we see out there, especially online? How can people tell what's credible and what's not?
That's the tricky part. Look for sources that cite their evidence, rely on peer-reviewed research, and are transparent about their methods. Be wary of sources that make sweeping claims or use a lot of emotional language.
So it's like being a detective looking for clues and red flags?
Exactly. And remember, it's always okay to be skeptical. Don't be afraid to ask questions and challenge the information you're given, especially when it comes to something as important as your health.
Well, this deep dive has certainly given me a lot to think about. It's a reminder that science is complex and that we need to approach it with a critical eye.
I completely agree, and this is really just the tip of the iceberg. There's so much more to learn and explore about this topic.
Thanks for guiding us through this complex terrain. You've given us a lot to chew on.
It's been my pleasure. And to all you deep divers out there, keep those questions coming, keep exploring, and most importantly, keep diving deep.
Well said. We'll be back soon with another fascinating deep dive. Until then, stay curious and stay informed. All right, so we've spent the last two parts really getting into the weeds with this RT-PCR test critique, but now I kind of want to zoom out a bit, look at the bigger picture.
Yeah, the forest instead of the trees.
Exactly, because at the end of the day, this isn't just about a test, it's about how we use science to make decisions that affect, well, everyone.
It's about the real-world implications, the impact these findings could have.
Right, because think about it. The results of these tests, they haven't just been numbers on a page. They've had very real consequences for people's lives.
Absolutely. I mean, people have had to quarantine, miss work, even skip important events based on a test that might not have been accurate.
It's been tough, that's for sure. And it makes you wonder, if the test itself is flawed, then what does that say about all the data we've collected using it?
Right, that's a huge question. It's like realizing the ruler you've been using to measure everything is actually a bit off.
So are we saying we should just throw out all the data we've collected so far? Start from scratch?
I don't think it's that simple. It's more about being aware of the limitations of the data, interpreting it with a critical eye.
So like taking it with a grain of salt?
Exactly. We need to be more cautious, look for other supporting evidence, and be upfront about the uncertainties.
Okay, that makes sense. But what about solutions? I mean, if we know this test has problems, what can we do to make sure we're getting more accurate results going forward?
Well, there are a few things we can do. For one, we need to address those specific flaws we talked about, like revising those primers and setting clearer standards for the cycle count.
So it's about fine-tuning the test itself, making sure everyone's on the same page.
Right. We need more standardization and quality control across the board. But I think we also need to start looking beyond the RT-PCR test. Explore other methods that might be more accurate.
Like what? Are there other options out there?
Yeah, absolutely. There are other molecular diagnostic techniques that might be a better fit, things like isothermal amplification or next-generation sequencing.
I vaguely remember those from our earlier deep dives. What are the advantages of those methods?
Well, for example, isothermal amplification doesn't require those temperature cycles that PCR relies on. So it's simpler, faster, potentially cheaper, and less prone to contamination.
Okay, so it's like a streamlined version of the PCR test.
Kind of.
Mm.
And then you have next-generation sequencing, which allows you to look at the entire genetic code of the virus, not just a small snippet like PCR does.
So it's like getting the full picture, not just a snapshot.
Exactly. And that can be really helpful for spotting new variants, tracking their spread, and even developing better treatments and vaccines.
Those methods sound pretty impressive. Why aren't we using them more already?
Well, there are some hurdles. Cost is a big one. And then there's the whole infrastructure thing. Not all labs have the equipment or expertise to run these more advanced tests.
Okay, so it's like having the latest smartphone, but not having the right charger or data plan to actually use it.
Uh-huh. Perfect analogy.
Mm,
But I think as technology advances and becomes more affordable, we'll see those other methods becoming more widely available.
I hope so. Okay, so we've talked about the problems, the potential solutions, but at the end of the day, what does all this mean for the average person who's just trying to navigate all this information and make smart decisions about their health?
That's the key question. And I think the main takeaway is that no test is perfect. No data is absolute.
So we need to be critical thinkers, not just blindly accepting whatever we hear.
Exactly. Question everything, seek out different perspectives, and remember that science is always a work in progress.
What are some things people can do to be more informed consumers of this kind of information?
Well, for starters, always ask about the type of test being used. If it's an RT-PCR test, find out about the lab's protocols, their cutoff values, those sorts of things.
It's like being a smart shopper, doing your research before you buy.
Exactly. And when it comes to data, stick to reputable sources. Government health agencies, research institutions, those are good bets.
Okay, so do your homework and be discerning about where you get your information from.
Exactly. And always keep in mind that context is key. A single data point doesn't tell the whole story. Look for trends, compare data from different sources, and be aware of the limitations of how the data was collected.
Well, this whole conversation has been a real eye-opener. It's amazing how much complexity there is behind something we thought was pretty straightforward, like a COVID test.
It's true. And I think this deep dive is a good reminder that science is always evolving. What we know today might be different tomorrow.
That's a good point. So the takeaway here is to stay curious, keep learning, and don't be afraid to ask questions.
Couldn't have said it better myself. That's what this show is all about, after all.
Well, on that note, a huge thank you to our expert for taking us on this deep dive.
It's been my pleasure, really.
And to all our listeners, thank you for joining us. We'll be back soon with another fascinating topic. Until then, stay curious and stay informed.